Hello everyone and welcome to Chapter 14 screencast. This is going to be a little bit of a review and we're going to make a play posit out of it so that you can complete some questions and get some extra points. So in Chapter 14 we're talking about acids and bases, and we had to take a trip back to memory lane and talk about that water molecule. Because we know a couple of things about the water molecule. As you see here, it's polar, which means it has slightly positive sides and a slightly negative side. And the positive sides are because the electrons that the hydrogens have spend most of their time around the oxygen with the oxygen valence electrons. They do come here a little bit, but most of the time is spent here. So what happens is, because the oxygen actually has these two more electrons in there a little bit more often, this side becomes negative and then the hydrogen side becomes positive. So that's one thing we learned about the water molecule. And then the other thing that we learned about the water molecule is that sometimes in a solution, what happens is that this water molecule will go through a split, a breakup. You know, here's the happy couple, and then they're going to break up. And the oxygen and the hydrogen, well, let's say that's the guy in our couple, and then this oxygen by itself is the girl. And they go through a split. And the oxygen and the hydrogen, they actually keep the electron from the girl that was part of the relationship. And they become known as a hydroxide ion because they have that extra electron in their negative, and the girl's so happy about the split that she's glad and she's very positive. It was the best thing to do, and she's lost the electron and she becomes positively charged. So we wind up getting these hydroxide ions and these hydrogen ions, and in a solution they tell us whether something is going to be acidic or something is going to be basic. So if we have more hydrogen ions in a solution, it's going to be more acidic, and if we have hydroxides in a solution, it's going to be more basic. So that's something that we have already known. So we discussed different acids and we called them Arrhenius acids. And one of the characteristics that we talked about is that in water, they're going to produce hydrogen ions. So this water should be over here and there should be an arrow, but for some reason it didn't copy correctly. So here's our hydrochloric acid, and if we add that to water, what's going to happen is that those hydrogen ions are going to split from the hydrochloric acid, and they're going to lose an electron, and the chlorine is going to gain that electron. So here's that hydrogen ion, and this is how we know that something is going to be acidic. When we take a look at the equation, we look to see if there are hydrogen ions that are available. So in Arrhenius acids, anytime we add water, it's going to dissociate. So here's H2SO4. Add it to water and we're going to get two hydrogens and we're going to get SO4 with a 2 minus. And these hydrogens are going to tell us that, hey, this is an acidic reaction that took place. So now the way that we name these acids are like follows. If an acid produces just a simple non-metal ion in water, then the prefix that we're going to add to it is hydro, and the N that we're going to put on it is ic. So for HCl, that's going to be hydrochloric acid. For HBr, that's going to be hydrobromic acid. Okay, so we're just adding the hydro, and we're taking the nonmetal's partial name, brome, and we're adding IC to the end. The acid HCN that produces H+, and the simple polyatomic ion CN, negative, so you got to go back and check your polyatomics for this, is also named with a hydro and an ic at the end. This particular one, because this is a polyatomic ion, this is cyanic, so it's going to be hydrocyanic acid. Okay, so here we go. We have HF. When that breaks down with water, it's going to have a hydrogen and a negative fluorine, hydrogen fluoride. Okay, so this is a little bit different because this is where we get a negative ion, and H2S, we're going to wind up getting 2 hydrogen ions and a sulfur, a 2 minus, because guess what? It's going to balance out, and that's going to be hydrogen sulfide. Okay? Little bit of a refresh there. I know I'm going quickly with this. We talked about oxyacids in the name game. And again, this deals with our polyatomic. If our polyatomic ion ends in ATE, then we're going to add ic in the acid form. And if the polyatomic ion adds in ITE, we're going to add OUS for the acid form. So here is an example. We have nitrate ion. We're going to add that hydrogen to it, and it's going to be known as nitric acid, because when this breaks down, it's going to have the hydrogen and then that polyatomic ion. Okay, so nitric acid. NO2, nitrite, so we have to add OUS. So we're adding the hydrogen to it, and it's going to be nitrous acid. So a sulfate ion, add the H to it, and we're going to get sulfuric acid, or sulfite, sulfurous acid. All right. And even if we have acids of halogens that have oxygen in them, again, if it ends in ATE, we're going to end in ic. And if it ends in ITE, we're going to end in OUS. So a chlorate ion, when it reacts with hydrogen, it'll form chloric acid. In this case, we don't say, like we did here, we don't say hydrogen. We call it by the polyatomic ion name, and we just add IC to it. Chlorite, chlorous acid. Okay, so there are some other oxyacids of halogen uses for prefixes that we talked about, and when we have one oxygen more than the ic, the acid is named with the prefix per. So here's hydrochloric acid, and notice that chlorite has one more, so we're going to call this perchloric acid. And the same thing here with chlorous acid. We have one less than that, and we're going to call it hypochlorous acid. Okay, so here is our table that we were referencing, and I said to you, please make sure that you be comfortable with this. You'll see it on the test.